afternoon session. So next speaker is Mika. He's going to talk about top-down lower bounds for depth for circuits.
Okay, thank you. Okay, so this is joint work with my students Artur and Anastasia, also Dmitry, Sokolov. All of them used to be at St. Petersburg, but now they're with me at EPFL for obvious reasons. Okay, so it's we have this new result in boolean circuit complexity. So maybe the model is partly familiar from the morning. So I draw circuits with all the boolean variables at the bottom. It's kind of important because I'm going to talk about top down and bottom up. And okay, so we have the usual and, or, and not gates, and then my circuit produces one bit of output at the top. Okay, so I know some of you came here for a cutting edge, high-end research talk, but we're actually just going to solve some exercises from an undergrad class. So this is an actual exercise sheet from this spring. So one of the questions I put up is, circuit complexity of the parity functions. If you have this XOR function, you put it n bits of input, and you're supposed to output yes or one if the Hamming weight is odd. I'm asking how to, how can you compute this simple function efficiently, even with just a linear size circuit? So, linearly many gates. So here's how you do it. This is an easy problem. So you can start with n equals 2. So I denote the XOR function with this blob. So I have 2 input bits, 1 output bit. How do you implement this with the usual Boolean gates? Well, here's one implementation. It's actually a DNF formula for it. But the point is n is a constant size circuit. So how do you do it in general? Well, here's how you can build this binary tree of these parity gates of fan-in 2. And now you just plug in that constant size circuit for each of these blobs. So that gives you a linear size circuit. And in fact, the depth is pretty good too. So order log n. In fact, that's sort of optimal. Like if I only give you and and or gates with fan-in 2, then any function that depends on all of its variables needs log n depth. So maybe it's a bit more interesting if I allow the and or gates to have unbounded fan-in. So like one does in a DNF formula. So this is another exercise from their sheets, but this is already harder. If we are to judge by what my students write on Piazza, this was the hardest problem, even with hints. So I'm asking to show that if you want to compute this parity function with just a DNF formula, so or of terms, each term is a conjunction of literals, then you need loads of them, so exponentially many terms. By the way, so I view a DNF as a depth to circuit. Always put the kind of negations next to the inputs. So I don't know, any takers? How would you solve this super difficult exercise? Ideas?
Each clause have all the variables.
Okay, so you're claiming that each term needs to involve all of the variables. And why is that?
So otherwise you'll get like 2 corresponding assignments. If you flip a bit, it should change the value of the XOR.
Okay, so I have here an example with n variables. So if I have a clause with n, it has only one satisfying assignment. But if one of these variables was not in there, I would create another satisfying assignment where I could flip the bit you didn't mention. So that would make the term accept both an odd and an even string, and that's a contradiction. So you would then cross the whole DNF formula to accept something that has the wrong parity. Okay, so that okay, so why? Okay, that's a silly question. Why does the theorem follow from this? Maybe the same person.
I mean, you need to the n-1 value to this.
Yeah, so if each term can only accept one input, and you have, well, this many inputs that evaluate to 1, then I just have to have one term for each of them. Okay. So yeah, we solved this without any hints. Very good. So maybe just to belabor the point, like what did we do here? We said the DNF formula, it's an or of bunch of terms. And the way it's computing my Boolean function, so Boolean function, bunch of yes inputs, bunch of no inputs. And the OR is a kind of, I view it as a kind of a union. So the OR kind of constructs the set of one inputs as the union of inputs accepted at the lower level. So, set of one inputs, union of, things that the terms accept. And just to really recap, we could say we gave a top-down lower bound argument. Could say, so I'm going to repeat the proof. Look at the top fan-in. If this fan-in M, if it's less than the number of one inputs, then there must be some term that accepts two inputs by this union. But if you accept two inputs, then you must have left one variable out in the term. And so this way I've found a term that kind of accepts both yes inputs and no inputs, and that's a contradiction. Okay, so I hope we are happy with our first circuit lower bound. Any questions about this? We just so that if the depth is really, really low, then you can't really save anything. You just have to brute force parity. So I guess now one could ask, like, okay, what happens? We know log n depth, you get a linear size circuit. Depth 2, you get, just an exponential size. What happens in between? So if we go higher from depth 2. So what's okay, let's do depth 3. What's a depth 3 circuit? What does it look like? Well, again, I just I put all the negations at the bottom. For each step, we have kind of two types of circuits depending on what the top gate is. But whatever the top gate is, the ands and ors alternate. Okay, so I claim that actually already for depth 3, you get an improvement. You can compute parity with in this size, which is, well, it's still exponential, but in root n. So how do you do that? So here's one way you can visualize it is I have my n bits and I bucket those n bits into root n buckets, each of size root n. So this is one bucket. And I first compute the parity of each bucket, and then I compute the parity of the buckets. So again, this is not an and or not circuit yet, but you could plug in for these parities their implementations as DNFs. So if I do that, so I just maybe replace this in this diagram. So if I replace this guy with its DNF implementation, so how large a DNF do I need? Well, it's at most exponential in the number of its inputs, and it has only n inputs, so you get this bound by just replacing the top object. So you could do that for actually each of these. Just plug in a DNF. So that would give you a circuit now. So DNF of a DNF, so that's, I guess, depth 4. How do you get depth 3? You need one optimization in my strategy?
Yeah, one layer CNF.
Yeah, okay, so you do maybe the top with a CNF. So just to spell it out, if you have CNF and DNFs, you get, very annoying, and or and. So you only get like 3 alternations of quantifiers. If you have 2 layers of gates of the same type, you can always collapse them to the same, like a single layer. Okay, so this pattern, you can do it, kind of annoying my drawings. You can do this for any depth and you get something like exponential in, well, this quantity. Okay, so one punchline is that this is tight. So we have known for a long time that this is for any constant d, this is exactly the complexity of parity. So the way to classically prove it, and there are a bunch of different methods. So maybe the most famous one is this switching lemma or random restriction method. There's also this Rasper-Smolensky polynomial approximation method that can prove lower bounds all the way to constant depth circuits. I just want to maybe highlight that these random restriction methods, if you know them, they're very bottom up. So what they do is they say, even if you have a very tall circuit, they just look at the bottommost couple of layers. Maybe they pick out a CNF from the bottom layer, and they say, if you restrict the variables accordingly, the whole function simplifies, or the CNF you picked simplifies with high probability. Actually, it switches to a DNF. So with a single random restriction, you can kind of crunch the depth of the circuit down by 1. If you continue invoking this sort of a lemma, you eventually kind of simplify the whole circuit. So this is how you can like prove lower bounds and identify limitations of constant depth circuits. But it's a very bottom-up strategy. So it's super powerful. People use it every day to prove lower bounds, not just in circuit complexity, but proof complexity and all over. But okay, so I personally also like an alternative method to prove these lower bounds, which is called a top-down method. So some kind of an argument that analyzes the circuit starting from the top gate. So these methods have been used a lot as well. Just a bunch of pointers. We can have top-down methods to prove lower bounds for formulas. I mean, we don't have super polynomial lower bounds for formulas, but some quadratic formulas size lower bounds, they can be phrased as top-down arguments. Top-down methods are very popular for proving lower bounds for monotone circuits. Okay, so without NOT gates. In fact, the earliest work there is this Karchmer and Victorson. They kind of they introduced what are called Karchmer-Victorson games. So it's a connection by which you can view circuits in the language of communication protocols, and somehow naturally that language is very much a top-down language. So many of these works that prove monotone circuit lower bounds, they also have they're often phrased in the language of communication complexity. Okay, so then there's a third type of lower bound result that top-down methods have been used for, and that's for depth 3 circuits. So we can do not just DNS but one more level. So yeah, loads of papers have used this, but for some reason, they were always stuck at depth 3. So we didn't know of how to use this top-down method to lower bounds for depth 4, and that will be our main result. I mean, spoiler alert, it's in the title, but yeah, I don't know. I mean, DNS like this are super interesting. And these are the next format.
There's also this result that if you get a very strong lower bound for depth 3, then you get it for you get a super linear.
Okay, so you can also say that general circuits can sometimes be compressed to constant depth circuits. So if you get strong enough lower bounds in this, that's one motivation. And also, I don't know. I mean, there's many applications. So depth 3 appears when you study the low levels of the polynomial hierarchy in classical complexity theory. That's where I've played around with these things the most. And historically, that's how these methods were introduced, actually. Okay, so I've highlighted here a particular work. This is Postad, Yukna, and Putlak. So they have a paper where they really kind of established this top-down method as a style of lower bound to study for its own sake. So they reprove some circuit lower bounds using this method, and they explicitly pose the challenge of trying to make this method work for depth 4. So that's the earliest mention of no, we're still stuck at depth 3. But I also want to kind of maybe correct some kind of a misconception I sometimes hear, let's say in conference reviews, that this paper is like invented the top-down method. I wouldn't quite put it that way. So I found like earlier papers that do top-down without like being too explicit about it. So the earliest I found, this is Baker and Selman. Let me just show you what that. Sure.
Are there low bounds for, let's say, depth 3 that you can prove it's a top-down approach, but that you don't know how to prove the bottom-up approach?
Yes. So I mean, that's actually one of the questions I have at the end. So there are some early results. It would take some time to say what the function is where the lower bound is proved, but yeah, there's like Artur
all the more recent, because there's tons of works here. So they do depth 3 top-down because they want to, or because the bottom-up doesn't work?
Okay, so I should say there's a very recent paper with my students too, where we want to pin down maybe the constant in the exponent. And so then you need very precise arguments, and that's where these methods are used to. There's also this satisfiability encoding lemma that gives like really, really tight bounds for depth 3 parity. Okay, so it's like a fine tool. I also I will motivate the technique later as well. Okay, so let me just flash this earliest paper I found that does drop down. So, well, they're motivated by separating the second level of the polynomial hierarchy relative to oracles, whatever that means. It's, you know, classical complexity theory, and they actually include this nice quote. It's from Hartley Rogers. I think this is the textbook on computability theory. I fond memories as an undergrad reading this. So he says, or views much of mathematics as a crutch for us to understand alternation of quantifiers. So human mind seems limited in its ability to understand and visualize beyond 4 or 5 alternations of quantifier. And I mean, I sort of agree. Like when you work on these things, it's like painfully obvious how you. Even though everything is elementary, it's so easy to get messed up. So I want to kind of put this up as a reminder for myself to go slow today, and yeah, hopefully you will interrupt me when I'm being too fast. Okay, so the result we now have is a depth 4 method, and as you know, we demonstrated to reprove this old lower bound for parity, so we get quantitatively basically the right answer. So it's just a new proof of an old result, and even more, it's even weirder than that, in that the method I'm going to discuss is complete, in the sense that there's a formal sense in which it can prove any lower bound that's true. So, this is a true lower bound, and there's sort of a non-constructive reason why there's always a top-down proof of it. So what we've only sort of done is, make that proof explicit or constructive. But, I'll discuss this a bit later, what it means to be complete. So this is not true of, let's say, the random restriction methods or polynomial approximation method. They're very powerful, but there are some, it's not clear that they can prove any lower bound that's true. So yeah, are we just like, why are we doing this if it's just like playing around with like known questions? I guess like I have some long-term goals. I mean, we didn't prove anything new, but I'm hoping we'll really start for new techniques in circuit complexity. So I'm hoping that doing something like this, you could in the long term settle some ambitious problems. So for example, we don't understand alternation in communication complexity. So the best we can do sort of is to prove lower bounds for non-deterministic communication protocols, but not for, so that's like exist blah, but not for all exist blah. So that's already a communication model for which we don't know how to prove lower bounds. And the random restriction method sort of completely failed there. An even easier goal is to show lower bounds for constant depth circuits that have a layer of parities next to inputs. Okay, you can prove some lower bounds using the polynomial approximation method, But what if I ask you to show a particular function like the inner product cannot be computed there? The problem is both these circuits and this function is both approximable by low degree polynomials. So you need some more specific technique. And showing lower bounds like this, they're sort of necessary to show lower bounds for the communication polynomial, which in turn is necessary for Valiant's rigidity program. Okay, so this is, I don't have any, this is just the kind of like research grant proposal style of vision, but at least we're taking some steps.
That's it for the last question. Can you put the depth 3?
So if I have DNFs of parities, we can prove, but not with one level more.
And then you said depth 4, how about depth 5? Is that anything on? Can we do anything?
So can we, does our method, so now we're stuck at depth 4. Again, it's one of the really annoying things about this. You'd think that if you find the right proof for depth 4, then mathematical induction kicks in and you can get it for all constant depths. Yeah. But I don't know, maybe we have the wrong proof still. So
the best bounds number say depth 5. Well, it's no. I'm thinking the other. Oh, okay, it is no.
Yeah. So we just don't know how to do it with top down.
Oh, okay.
Okay. Yeah.
This is a proof things for functions which are for which random restrictions not all.
Well, maybe I sort of vaguely claim that there are, I think to ask previously, there are some functions where we don't know how to prove them with a random restriction method, but a top down, but they're like depth 3 results already. Okay. So okay, so I want to prove this, but of course, like our depth 4 builds on depth 3. So I want to revisit how people have used top-down methods to prove lower bounds with depth 3. So there are a couple of ways to prove these things. My favorite and what we build on is a technique that uses something called bit unpredictability. So, so I guess now is the time to kind of wake up, internalize this one key idea, then you can go back to email and TikTok. But just this is the take-home message. So I just read somewhere that every good talk should have one key idea. Our proof has 2 ideas, but I've just chosen to place one of them as the key idea. And so this is actually from an earlier paper already by Myron Victorson. So so their main result is some kind of an information theoretic lemma. So it doesn't say anything about circuits, but actually, and we'll go over this, it's a mouthful, but this is easy to apply to get the tight lower bound for parity for depth 3 circuits. And yeah, what I really like about this is that you don't need any background. It's just pure combinatorics information theory, and it's sort of applicable for circuit lower bounds. Okay, so let's see what this is trying to say. So it says that if I have a large set of bit strings, so I measured the size of a set through its entropy. So think of this maybe uniform distribution on the set. So identify X with a random variable uniformly distributed over it. So if this is a large set, so that the entropy is very close to n, but okay, maybe you have entropy loss, something small, the best number you can put here is actually root n. But yeah, think of this as n to the epsilon. So then if I pick a random element from my set and a random coordinate, then this coordinate will be unpredictable to it's hard to predict this coordinate from just looking at few other coordinates of the bit string. So if you sample these at random, then with high probability, the ith bit of the random variable, it remains unpredictable. So it still has entropy. So it can achieve both values 0 and 1, even if I condition some small subset of other coordinates. So for any subset of small enough size, subset that doesn't look at the ith coordinate. Now, if I condition my random variable, according to, this sample, I'm looking at this small window. Well, it still does not kind of predict the ith coordinates. Both values are possible.
Why is root n the best option?
Come again?
Why is root n the best variable for that?
Okay, so yeah, I claim that this tight. So I can give you an example where this starts failing if these numbers are, well, like order root n. Actually, a weird way to see this is optimal is that I'm going to apply this lemma to prove the circuit lower bound, and the circuit lower bound is optimal because it's exponential in this number. Okay, but let me.
I mean, basically what you mean is that both these numbers.
Yeah, so
You can only get that one spot. Right?
yeah, you can parameterize them and say that the product of these should be sublinear. So here's an example that shows this is optimal. And yeah, it's a good reason to kind of mull over what this is saying. So I arrange my n bits in this root n by root n matrix, and then I say that in each row, I fix the parity of each row. So maybe I fix all of the parities to zeros. Okay, so my set X is just this subspace that has these parity restrictions. So how large is it? Well, I have all the strings except I've imposed root n parities. Okay, so this is like entropy exactly n minus root n. And now I claim that I can't predict anything, not with hyperbole. Just for no x, for no I, can do I have unpredictability? So I can predict. So you give me any position of a variable. Let's pick this one, and I claim I can predict the value here by reading. Well, if I'm allowed to read root n variables, I can predict it. So. And what do I read? So I can't read this bit, but I want to read some other. Yeah, so I guess I just consider my I will be all the other things in its row. So I know these values, I automatically know what this should be. Yeah, so you can even say it's like almost unbiased. For us, we just want, it suffices that we get full support for the variable. Okay, so yeah, let me explore this a little bit further. So the proof of this is this long. I don't know, at the end, maybe I can prove it. It requires one counterintuitive idea, but it's otherwise quite short. Let's see if we get there. For now, maybe I want to try, let's just play around with this lemma a little bit more. So I'm just going to rephrase, what does the lemma say? Okay, so here I have my set of bit strings. So each row is a bit string. And I applied the lemma to this set. So that means if I pick a random element from the set, I pick the final one, and a random coordinate, maybe I pick this blue going. Okay, so if these are typical choices, the lemma says that bit is unpredictable. So, okay, what does it mean? It means I can, yes, there's one way to apply the lemma, is, okay, maybe I take my chosen bit string and I flip the one bit that was unpredictable. I claim that what I get by doing this is something called the local limit of this set of strings X. So a local limit in this says that if you look at my string here in any kind of local place, you're going to find some string in this set X that agrees with it. So, okay, if I look at, well, if I look at things outside the one bit I flipped, then obviously the green guy will agree with it. So that's not very interesting. So let me look at another local view that involves the bit I flipped and maybe some other variables. Well, because the green guy was unpredictable, it means that the pattern 1, 1 here, it was such that just conditioning on 1, 1 does not predict the blue bit. So what it means is that there's some other string in the set. I mean, I guess it happens here that has the 1, 1 pattern, and the blue coordinate is, has the opposite value. So, both guys are possible. So again, no matter which few coordinates of this vector I consider, I can find some vector in X that agrees with, it has the same local pattern. So, why is this useful for circuit complexity? Well, it's because this fools low width CNFs. Okay, so if I start with this, bag of n-bit strings that are all accepted by some, low width CNF, so one low width CNF, it accepts all of these strings. Well, I claim it also then must accept this local limit that I created. Okay, so why is that? So what does a CNF do? So CNF says I accept my input if there's a bunch of local checks that need to pass in order for me to accept my input. So each local check involves at most this many variables. And I claim that, well, the local limit is accepted because whatever local check you perform here, whatever few bits you consider, a check must pass there because that local view is found somewhere in this set. And here the checks always pass. Wonder if that was clear. So do we buy this claim that these sort of local limits, if I have seen accepting all of these, I kind of get more strings that are accepted. I have another, just to illustrate this concept a little bit more. So this is just like a formal definition of what I mean by a local limit. It's just what I said intuitively. So I say that this a string is a local limit if whenever you look at it locally, so you pick some k bits that you're looking at the string, and that pattern is found inside the set X. So there's some little x in X that also has the same pattern. So that's just the formal definition. Okay. So for arbitrary set X, I can sort of close it under these local limits. We just argued that if a CNF accepts X, it accepts all its local limits. That's all we need for these lower bound proofs. But let me just say that these limits they're a very natural notion. They sort of exactly capture the power of CNFs. So maybe this is an aside comment towards the completeness of the method. So if you want to fool CNFs, if you want to say my CNF accepts this bag of strings, and I want to argue it accepts some other string, it needs to be a local limit. So if you collect all the local limits for a particular set, you're actually getting the smallest set that includes your original set, and moreover is a set accepted by some KCNF. Sorry. So a particular one. Okay, maybe I should not belabor these slides too much. For us, it's just the only thing I want to take away is that what does the unpredictability lemma say? It says starting from the set X, if I pick a typical point in there and I flip a typical bit, I get a local limit. That's what the lemma says. Maybe I don't get all the local limits, but at least some of them. Okay, so I want to show how this lemma then is applied to get the depth 3 circuit lower bound. So let's try to do that. So it's actually quite simple. Okay, so top down, I start analyzing my circuit from the top gate. So I assume I have two good to be true circuit computing parity. So I know at the top gate, the circuit, okay, correctly computes parity. So it accepts all of the yes inputs, that's in green. It rejects all of the zero inputs in red. Okay, now I need to take a step down the circuit and try to find, some kind of a contradiction lower down the circuit. And I'm just going to do a very naive step. I'm going to pick one of these subcircuits, or in this case, CNFs, that accept the largest fraction of yes inputs. So if you remember, it's the OR is like a union, the set of one input is constructed as a union of what is accepted lower. And I'm just going to jump to the CNF that accepts the largest possible fraction of yes inputs. So, okay, a little bit more quantitatively, if my circuit was of size or exponential in n to the epsilon, and this argument is going to work for epsilon up to root n, but just for intuition. So then it means that I can find some subcircuit that accepts this, 1 over this fraction of the set of yes inputs. So that just translates into saying that, I can find a CNF that accepts this set X, whose entropy is very large. Yeah, so this is exactly something I can plug into the unpredictability lemma. I found a CNF accepting many bit strings. Okay, moreover, so I'm making one simplifying assumption, assuming that the width of the CNF here is low. It's typically something like n to the epsilon, like log of the circuit size. I guess in an arbitrary circuit, it doesn't have to be this small, but if you have clauses with much larger width, they sort of contribute very little. They can be ignored. They contribute very little to the picture. So it's like the interesting case is when the width also of the CNF is roughly the log of the circuit size. So allow me to assume that. Okay, so now we just apply. We just apply the unpredictability lemma. This is a large set, so it means if I pick a typical point, flip a bit. Okay, so if I flip a single bit, I change the parity. So then I get a local limit that's, well, has the wrong parity. It's a local limit, so the CNF still accepts this limit. So now I've found that this CNF makes a mistake. It accepted all of these, but actually it also accepted something from the wrong side of the function. Okay. Questions about this step 3? That's it. You optimize this, you can even get this root n bound here, but it's more or less clear.
Do you also get average case lower bound?
So yeah, average case lower bounds is somehow we're going from depth 3 to depth 4. The average case lower bound is somewhere in between, I would say. So yeah, to get average case lower bound, I think you need the new methods that we have. That's my vague recollection. More questions?
What was the error in the higher probability refixing the exponentially small in the?
So what is the probability that you're successful with 1 over order? So this is the actual statement. So k times d is sublinear. Oops. Then yeah, for this argument, you don't actually need that quantitative tightness.
I will use the sensitivity of the parity.
I guess, yeah, we didn't use much of the parity except this. So yeah, if I even had a function with very high average sensitivity, I guess this would still go through. Yeah, it's important we understand this step 3 well, because I'm going to switch to step 4. One more question before I go forward. Yeah, so maybe a slightly different argument. Yeah, it's certainly in the literature.
If this proof method is complete, why can't it be depth bigger than 4?
Maybe I'll address
Yeah,
it at the end.
You can, right? Like if it's completed,
Sure.
it has to be able to prove it.
Yeah, but yeah, maybe I discussed at the end. So, so far, I mean, it seems pretty straightforward. Let's see, like, what the complications are for depth 4. I mean, again, there must be some because it wasn't that easy. Although in hindsight, I think you'll see, we just about have the tools to do this with our paper is quite short, like 10 pages. Okay, so let's do depth 4. And again, top down, so it started at the top gate. So now it's an AND gate. Okay, so, you know, at the top, I compute all the yes inputs correctly, all the no inputs are rejected. And I again do a step down the circuit. So what kind of a step? Previously, we did this greedy naive step where we just took the sub-circuit that accepted the most yes inputs. Okay, we have an AND gate, so now we want a sub-circuit that rejects a large fraction of no's. And in fact, in our proof, we still follow the naive strategy where, you know, we just pick the sub-circuit rejecting the most strings. So that's what it looks like. We didn't do anything clever yet. But let's see, you know, what happens for the next step. Which sub-circuit should I pick? Let's see what happens if I do another naive greedy step. So it's an OR gate. So the set of yes inputs is constructed as the union of what is accepted here. Let me choose a sub-circuit that accepts the largest fraction of yes inputs. Another naive step. Okay, so far so good. Now we just know we have a CNF. It accepts all the green things. It rejects all the red things. Otherwise, I don't have any guarantees. So now, you know, let's apply this unpredictability thing again. I mean, I have a good sizable fraction of accepted strings here. So, you know, let's apply the unpredictability lemma. Problem. To reach a contradiction, I really need to say that, you know, you can't simultaneously accept these and reject these. So I would like to say that the green guys allow me to construct a local limit that's in the red set. But so far, I haven't been careful enough. It could be that this situation happens. I've gone down the circuit so much that the limits of the green set, you know, they're just disjoint from the red. I didn't reach any contradiction. So, I mean, let me ask you, how would you fix this? Like, maybe rewind one step. So go up one level. Where should you step down to try to avoid this issue?
You need some distinction on the one in just by doing middle step in the red.
Yes, so Shahar is saying that I want to choose a subset that's somehow aware of this set. And this is the first modification is we need to define a sort of a mirror image of the red set. So some kind of a set of yes inputs that's sort of locally or, you know, somehow computationally indistinguishable from the red. So we just call it the mirror set, like somehow it's like the analogous set, but just the answer is reversed. What would you propose as the mirror set? So here I just have an arbitrary set of a large enough density. Now, which sort of inputs on the other side of the function should I consider? I mean, I'm taking suggestions for what could be this mirror set.
Are you not just going to take things which are one bit flipped from something in the red?
Okay, so that's a good suggestion. I was hoping for that. Okay, so we have this red set, and a common intuition is I usually think of these sets. All I know about them is that they have, you know, good density. So they might actually be error correcting codes. So maybe the red set looks like this in this, you know, boolean space. And the proposition, okay, what kind of a set would be difficult to distinguish from this is, well, for each red set, maybe I consider flipping each of its coordinates. So, you know, I flip the first coordinate, I get some green guy here, second coordinate. So maybe the green set will look something like this. So yes, so this is like the attempt you first try. And I think, or Myron Victorson also tried this, that they was motivated to try to find this depth for proof. But somehow the reason this is difficult is, I mean, why are you proposing this? It's because you'd like to construct these local limits starting from a green point, you know, jumping as a local limit back to the red. But the problem is, for this green guy, there's only one coordinate that leads you back to the red set. Whereas the unpredictability lemma only allows you to flip like a typical coordinate, not the special one that brings you back to the red guy. So in short, I don't know how to make this definition of mirror set work. And certainly, you know, this idea of applying the single bit flipping lemma sort of runs into this issue. So I'm going to adjust the definition of a mirror set a little bit. So here's the definition we will take. I want a bunch of yes inputs. And well, instead of looking at its immediate neighbors, I just look at a larger Hamming ball. So maybe I look at the ball of radius, okay, some clever cube root of n parameters around x. Okay, the Hamming ball of that radius, and I ask, how many red points are there? And if I get many, I'm going to include this in my mirror set. So, you know, my mirror set, it's just points such that in my Hamming ball of a certain radius neighborhood, I get many red points. Okay. So this is our first attempt at a definition. Okay, so once you've defined the mirror set, now you just apply the same kind of, now we take the greedy step, you know, give me a subcircuit that accepts a large fraction of the mirror set. Okay, so the picture is something like this. So I have a CNF, it accepts a large fraction of the mirror set, rejects all of the red set. Okay, so now what is the final step that I'm shooting for? I want to use this set to construct a local limit in this set. That's my final contradiction. Okay, so this is the goal. Okay, I have this set. I want to construct, these very specific local limits in the red set. Okay, so we sort of we have like two new challenges. So one was this, construction of a mirror set. That's sort of we solved. Another is it's no longer enough for me to just flip individual bits, because I don't know if there's any red points directly next to me, but I know there are loads in a good distance away from me. So for the local limits, I'm not going to flip individual bits, but whole blocks of bits, like jump a little bit further. Okay, so these are like the two challenges in the proof. I've addressed the first challenge of a candidate mirror set. Let me address the second challenge. So how do I, how do I construct local limits that I can obtain by flipping a whole block? Well, we just generalize this Meyer-Victorson lemma to whole blocks of bits. So it's a natural generalization. The parameters change a little bit. So now, you have 3 times the cube root of n appearing. That's, by the way, optimal for this lemma. So yeah, you have the same setup, but then instead of looking at an unpredictable coordinate, you look at a whole block of coordinates. You choose this like cube root of n many coordinates at random. And you would like to say this block is completely unpredictable from other bits. So if you look at bits outside your block, and condition with that, then, well, you can't predict much or anything really about these bits. So you get the full support. So all possible bit patterns on this block B. Okay, so, you know, it's a kind of a natural generalization of this lemma. Okay, so, you know, we sort of hope to apply this to the green set to get these like bigger jumps. Okay, so, but I still have to kind of land inside the red set. So here's the final part of the puzzle. Okay, so again, I had this dense red set. I constructed my mirror set of these green points, and I made sure that, well, in the like vicinity of a green point, there are many reds. And applying this lemma from previous slide, I also know that for typical green points in the set, like, you know, maybe the all zeros one, the lemma applies. So it means that I can flip a large block. I mean, if I choose a typical block of this size, it will be a local limit, or any modification inside that block is going to be a local limit. So how can I now jump from the green point to a red point? Show that one of these red points is a local limit. So here's exactly the condition I would like to have. So again, I mean, suppose the lemma block unpredictably applies for the green point. So that sort of means that for most choices of a block, I have my like local limit thingamabob. And it would be fantastic if I could, you know, jump to a red point, which means that I have a red point that I can jump to by only modifying the points in B. So sorry, I changed the notation a little bit. I'm thinking not of bit vectors, but indicators where the one positions are. So I think this is the empty set, and, you know, if I flip a random block like this, I get a local limit, but I would like to jump to one of the red sets. So if I get this probability, this condition with high probability, then I'm sort of done, because I have two high probability events like this, and then, you know, this is, you know, satisfies the lemma with high probability. So how can we ensure? I mean, okay, guys, like what is this condition I've written here? Brian, does this look familiar? Or Shahar or Anup, maybe?
Satisfying.
Yeah, so okay, so this is just sort of the definition of what a robust sunflower is without a core. And so it's exactly what we need. Like when we were working on this popped up pretty naturally. It's not like we had this tool and we were trying to hit this problem with it, but it just goes naturally.
Satisfying. Yeah.
Yeah, so I really need this property. I mean, it doesn't hold for any point. It doesn't even hold for points that I define this way. But, you know, all this work on sunflowers, lemma says that if you have such a, you know, a point with, you know, a dense, many red points around it, okay, so maybe this condition is not satisfied for X itself, but it's satisfied if I kind of remove the core of a sunflower, which in our language just means moving the green point a little bit. So that's okay. So now I don't lie anymore. This is the final definition of the mirror set, is that you kind of start with this set and then you just like move the point a little bit so it becomes this the core of a sunflower. So then you can ensure this property.
This is just a satisfying thing.
Yeah.
Quantify.
Okay, so that's pretty much it. So the proof just combines this unpredictability and sunflower. I guess, so I mentioned that this top-down proof method is complete. Maybe I'll skip the discussion, sorry?
Core of the sunflower does it have to be small?
Good point, yeah. So with these parameters, it turns out it's always small. So correspond to just a slight movement of the green point.
Mika, could you have chosen the red set different, like, you know, you chose the red set greedily and then you chose the green set in a special way for the red set. Could you have like chosen, would it still count as a top-down method if you had like, I mean.
Yeah, you can be more clever in the first step. I just don't know how you would do. So I've sort of finally formalized what a top-down method is. Like you retain the green and red set. Each point you define a distribution on one set, and what your return is a large fraction of that. So you kind of move to a subcircuit that accepts a large fraction of your original x. And what's complete about this is, well, the mirror set is sort of the distribution here. It follows some linear programming duality. There's always a choice of a distribution. If the lower bound hold is if you can't, you know, construct a set of yes input as a union of few sets except it lower down, there's always a distribution that kind of witnesses that hardness. It's just very, you know, this is non-constructive. So what we've only done, like when you instantiate this, you have to define the explicit description of the distribution. That's sort of what it means to keep a top-down method, in my mind. Okay, but I did wrap up. So the obvious
distribution there doesn't depend on the circuit, right? It depends on the class it is at one level below. Or no, oh, no.
So distribution is not supposed to depend on the lower level. You're not allowed to look lower down. You're only allowed to say, you know, you have these sets, you define the distribution, and then adversarially I return, you know, any circuit that accepts a large fraction of that. That's sort of the game. Yeah. I mean, this is not in the literature anyway, but this is how I think about it. This is what counts for a top-down method.
That's why it's called top-down.
Yeah.
The completeness, it's like approximate, right? It has like.
Okay, so yeah, you do lose some
That's fine.
factors, polynomial factors. Okay, let me end there. Thank you.
Why 4?
Yeah, I mean,
Why not 5?
so we got this result earlier this year, and then we tried to extend it to higher depths, but we're just stumped. We don't
Like
know.
some sort of sunflower type, like you could do something about higher. Something we're actually thinking about at some point. Like you have a per-second system, it can be more than like log spread, but having a system that satisfies some sort of. I don't know if this would help you. Like every 3 elements per sec or something like this. You think it's like log spread.
Yeah, so I don't know of any kind of. I don't even. Yeah, so I lack the method. I don't have candidate definition of mirror sets and.
Okay, so just everything just doesn't work because, or just a small number. That means some predictability only has 3 slots.
Yeah, I don't know what would be the unpredictability lemma 1 level higher. I don't know if there is one.
Maybe an easier question is your depth 3 with parity. Should be easier than that.
You just
5.
so sad.
So you look at this, right? So in the product in AC0 with parity, and you said currently we only not do it for DNF composite parity. So then before going to depth 5, you can look on depth 3 AC0 composite parity.
Yeah, I think it's an incomparable question, but could be. Yeah. So yeah, I think this is pretty tough. I mean, it's one of my sort of favorite open problems too. It's so yeah, at least personally a motivation for me to do the work right now.
Is there some, well, first, maybe I remember this incorrectly, but if I remember, if you prove more than 2 to the square root n for depth 3, then you start to get like these linear log depth lower bounds and variance.
Yeah.
So is there some barrier for these techniques to cross 2 to the squared n, or is that just
Well, I mean, not for the top down because it's complete, but yeah, it's true. The best we have are the bounds you see for parity. So it's hard to say like what is the thing we're hitting up against.
The barrier is the function, right? Like you need a harder function.
As well, yeah.
Oh yeah, I mean you yeah. Essentially tailor the function to that. Well, anyway, so you don't see any.
Yeah.
you also entropy guarantee in your lemma?
So for this like block unpredictability, whether we just said you get full support, but do you get maybe close to uniform on that block? We didn't work it out, but I presume you do.
Right. Not any questions? Let's thank Mika again.